This video is part 2 of a review of integration techniques. If you didn't see part 1, go ahead and click the link that should appear in the upper right hand corner, watch that first, and then come on back. In this video, we will do some error analysis and look at some common mistakes that students often make and the right way to do it instead. For problem number 11, one of these statements is absolutely true, and the other one needs some work. Can you tell which one of these is correct as is? When we integrate quotients, sometimes we go immediately to use substitution, but other times we use inverse trig rules such as these. So how do we know whether to use inverse trig rules or whether to just try use substitution? It's all about the degree of the numerator versus the denominator. For example, for part A, the degree of the numerator is 0. There are no variables up there. The degree of the denominator is 1. So the denominator wins by 1. Compare that with part B. The degree of the numerator is 0, while the degree of the denominator is 2. Notice the x squared. The denominator wins by 2. So this is the difference. When the denominator wins by 1, we will do direct substitution right away. When the denominator wins by 2 or more, that's when we use these inverse trig rules. So we have two different scenarios here. One of them, we're going to do direct substitution, the part A. But part B should be inverse trig. And we do not see inverse trig. It just says natural log. So that means that this is the one that is wrong. Here is the memorized rule that was used for part A. We know that the integral of 1 over u du is the natural log of the absolute value of u plus c. So using our mental u substitution, we see that we have the integral of 1 over u, where u is x plus 3. Since u prime would just be 1, we can do mental u substitution. And we can go straight to this, the natural log of the absolute value of u plus c. So here we go, the natural log of the absolute value of u plus c. So that's why part A is correct. Part B has no square root in it and there's a plus sign. So we know it's going to be the arctangent trig rule. No u substitution is required because we already have x squared and that matches up with the u squared. It doesn't matter that the order is reversed based on compared to the rule because addition is commutative, so the order does not matter. If this was subtraction, the order would matter. What we do need is the a value. The a value is always the square root of the constant. So in the back of your mind, you need to be thinking the a value is going to be the square root of 3. With that, we can go ahead and just employ the rule. So the integral should be 1 over a, so that's going to be 1 over the square root of 3, and then arctangent u over a. So arctangent, there was no u, so it'll just be x over a, x over radical 3, and then plus the constant of integration. In number 12, part A, we have the memorized rule. We know that the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. So that's correct. Part B is a common mistake. You can see what the person was thinking. If we do, if 1 over x leads to the natural log of x, wouldn't 1 over x to the third power lead to the natural log of x to the third power? Well, no. This rule only works for 1 over x, or 1 over u. If you have x to the third power, you need to do something different. Let's start by rewriting the problem as the integral of x to the negative 3 power dx. Now we can use the power rule of integration. So here's my x. I am increasing the exponent by 1, so I will have negative 2. Now I must divide by my new exponent, so I get negative 1/2. And then I have the plus c. So I think I'll go ahead and write my final answer now. So I will write negative 1 over 2x squared plus c. So this is the correct answer for part B. For number 13, parts A and B end the same way. They both have this same exact expression, and luckily they have the same answer, arctangent x, and of course plus c. And that makes sense because this is a perfect match for the rule. So yes, that's where the arctangent is coming from. So the mistake in one of these must be from the first part. So let's focus on that. The first part is just the memorized rule though. We know that the integral of 1 over x dx is, wait, I see the mistake now. I started to say we know this is the rule and this is definitely correct. But what is missing is the absolute value. Hey. The rule says the integral of 1 over x dx is the natural log of the absolute value of x. So that might be the only thing that was wrong. Let's consider the other one and just double check it. For part B, just focusing on this part only, we would do a rewrite and we would say, okay, let's talk about the integral of x to the negative 2 power dx. And then we would do the power rule of integration. So increasing the power by 1, we would have x to the negative 1 power. And then we would divide by this new exponent, which would give us a negative 1 in the front. But negative x to the negative 1 power is the same thing as negative 1 over x. So part B is correct. So it was just the absolute value symbol that was missing. A common mistake though, so be aware and be careful. This is like playing a little game. Look at number 14, part A and B. Can you figure out which one of these is wrong? Like what's wrong with this picture? Look at it for a few seconds. So obviously in part A, we have arcsine. So this should be the arcsine formula over here on the left. Is it? And for part B, I see arcsecant, and this should be the arcsecant formula. So does this match the formula, or which one of these is a little bit wrong? Let's start with part A and do a side-by-side comparison with the actual formula. So we have 1 over the square root of a squared minus u squared, and that compares with 1 over the square root of 1 minus x squared. That looks like a perfect match where, well, u is just x, and a should be 1. So in that case, if we were to do the rule, arcsine, you know what, there's the problem right there. We already see the problem. Arcsine doesn't have any absolute value in it, does it? So arcsine is just u over a, which in this case would just be x over 1. So this would be correct without the absolute value. So this should be, let's cross this out and write arcsine x plus c. Now it's correct. And that is a common mistake. On the other hand, arcsecant does have the absolute value in the formula, so this matches up all the way. Look at number 15 for a few seconds. Can you tell what's wrong with this picture? Well, they are trying to use what I always refer to as the a plus b over c rule. So here's what I mean by that. If I have a plus b over c, I know that can be split up into two fractions by doing a over c plus b over c. So if I ever see this, I can split it up that way. However, it has to be a plus b over c. If I had something that was like c over a plus b, I cannot split this up into c over a plus c over b. So the mistake is where they tried to do this, and this is no good. So hopefully now you see that part A is the one that's fine. We have cosine x plus 2 over sine x. That's like a plus b over c. So yeah, we can split that up into cosine over sine plus 2 over sine. This is the one that is wrong. So what should we do instead? We would do a u substitution where we let u equal the entire denominator. So this would be sine x plus 2. That would be u. And in that case, u prime would equal cosine x. Now we can do the substitution. So we would say that the integral of cosine x over u, and instead of dx, we will write du over u prime, which is cosine x. Then we notice that the cosine x in the numerator will cancel with the cosine x in the denominator. So that leaves us with the integral, that's a bad integral, but the integral of 1 over u du, which we know to be natural log. So we will have the natural log of u plus c. And the u was sine x plus 2. I didn't leave myself enough space. Okay, well, you know what? I'll put it right up here. So the final answer should be the natural log of the absolute value of sine x plus 2. All right, plus the constant of integration. There it is.